So what we're going to do in this video is graph absolute value functions. So we've already encountered absolute value functions when we were sketching graph translation theorem with parents. However, in this video we're going to go over graphing absolute value functions in more detail because when we did them in graph translation theorem, they were just rough sketches. So what you're going to be responsible now is if you're asked to graph an absolute value function being in more depth than just a rough sketch. So first thing, let's go over just what the parent was again. Remember, the parent is when you just take an input, take the absolute value of it, whatever you get as the absolute value is your output, and the domain of the absolute value, domain is valid input. Your domain is all real numbers because there is no real number that you can plug in and ever get something that is not real. For us right now, not real means taking the square root of a negative number, and that actually extends to taking the 4th root, the 6th root, the 8th root. An even root of a negative number is not real, as well as getting 0 in the denominator of a fraction, okay? So that can never happen here. And your range is y is greater than or equal to 0 based on what it means to be taking the absolute value. Now, in parent functions in graph translation theorem, we talked about the critical value was 0, 0, but I'm going to call it the vertex here. Is there something special happening at that value? And I'm just going to be go in a little more depth, and I'm going to have 5 points in my table of values for the parent. Now we already know what the parent looks like, okay, but I'm making a table of values because I want to show you something, okay? So I'm going to plug -2, -1, 1, and 2. Remember, when you need to graph a function, you need to plot points, you need to make a table of values. You pick x values that fall in the domain, and then you plug them into the function and you get their outputs. Now, I specifically chose these values, and I'll talk about them in a minute. When I plug in -2, I get 2. Plug in -1, I get 1. Plug in 1, I get 1. And plug in 2, I get 2. Oh. And this makes a V shape. So notice I have -1 and 1 are my inputs, and they give me the exact same output. That's going to happen every time that you have points that are equidistant from the vertex of an absolute value function. 2 and -2 are equidistant from the vertex. That's why their outputs are the same. Okay? Think about absolute value on a number line when you studied in an Algebra 1. Okay? You can be x units away from the balance point on the right and the left-hand side. Okay? They're going to give you the same outputs. Now, a V shape indicates that these branches, I consider this the left branch, the vertex, the right branch. The branches are linear. They have constant rates of change. Okay? As x goes 1 unit, y will constantly increase by a certain value. So what that indicates, okay, is that these are linear. So you can calculate the slopes of the branches. I specifically chose, if you look in your table of values, right here, I chose 2 points that fell on the right branch. I chose 2 points that fell on the left branch, which means from my table, I could generate the slope of the right branch and the slope of the left branch. So if I wanted to do that, okay, I would take these 2 points right here and I would calculate the slope between the two of them. So the slope of the right branch is change in y, 2 minus 1, over change in x, 2 minus 1, 1 over 1 is 1. The slope of the right branch is 1. If I wanted the slope of the left branch, I can calculate it because I have 2 points on the left branch. So that would be 1 minus 2 over -1 minus -2. That's -1 over 1, that's -1. Notice they're opposites. Right branch is 1, left branch is -1. Okay? So having 5 points, 2 on the left branch, the vertex, 2 on the right branch, is enough to tell me where the vertex is, as well as tell me about the slopes of each branch, which is enough to give me everything I need to know about an absolute value in detail. So what you're going to be responsible for when we graph these is stating the vertex, having 5 points, graphing it, and the domain and the range. So let's get started. And as we go through these, I will give us some more information about what will be required and how you should be doing these problems. Okay, so number one. Okay, so for number one and the following problems, you might want a calculator, okay? So if you want to pull up the just calculator on your computer, or if you want to grab your scientific calculator, you might want to have that handy for these problems. So first thing we want to do is I want to grab the vertex. So that vertex is a special point, okay? What's so special about it again is that there's only one x that has a unique output, and that's when x is 0, okay? And what does it give you? It gives you that unique output of 0, okay? So knowing when you get that output of 0 is going to be the vertex if you forget about all of the transformations that happen to y. So what's important when finding the x coordinate of the vertex is going to be what makes x plus 3 equal 0. Okay, so if I subtract 3 from both sides, I get x equals -3. So the x coordinate of my vertex is -3. Okay, now if I plug -3 in, I'll get the y coordinate. So if I plug -3 in, -3 plus 3 is 0. Now remember, you intentionally just solved for the value that would make this 0. So what's the absolute value of 0? 0. -2.1 times 0 is 0. 0 plus 1 puts you at 1. Okay, so we make a table of values, and -3, 1 should be in the middle of the table. So now 2 points on the left branch, 2 points on the right branch. So if I'm on the left branch, I should be plugging in x values that are smaller than -3. So I don't want to go crazy because I don't want to be making a huge table, a huge coordinate plane. So I'll pick integers that are close, -4, -5. Now I'm going to pick out my next points on my right branch in a specific way so that this is a little bit easier on myself in terms of how much work I have to do. -4 is 1 unit from -3, and -2 is 1 unit from -3. So if I pick -2 and -1, which are greater than -3, these 2 points do fall on my right branch, I have only 2 pieces of inputs that I need to actually plug in because these are equidistant from the vertex, so these will have the same outputs. And -5 and -4 and -2 will have the same outputs, and -5 and -1 will have the same outputs. So if I plug in -5, I get -2.1 times the absolute value of -5 plus 3 plus 1. -5 plus 3 is -2. The absolute value of -2 is 2. So this is -2.1 times 2 plus 1. Okay, so you can use your calculator and find what -2.1 times 2 is plus 1. It gives you -3.2. And -5 and -1 are equidistant, so that means the output of -1 is also -3.2. And -4, plug that in. Okay, evaluate the absolute value of -1, that's 1, so this is going to be -2.1 times 1 plus 1. And so that is going to give us -2.1 plus 1, which is -1.1. Okay, so we've got our 5 points. -3, 1, -5, -3.2, whoops, -5, -3.2, -4, -1.1, -2, -1.1, and 1, -3.2. And I know we don't, if you're using a ruler, that's great. These should still be going in your notebook. Okay, the domain here is all real numbers, and to look at the range, we want to look at, okay, our y-coordinate of our vertex. We're either going to be growing from that value in terms of our y-coordinates or getting smaller, all of our y-coordinates that make up our shape. And if we look at our graph, we can see that we are falling from the vertex, so our range is, we're only going to get outputs that are less than or equal to 1 based on this function. Now, something to look at, okay, to start observing, if I got the slope of the right branch, okay, so if you want to write this down, you can. However, this is not required to do every single time you graph. If your goal is just to graph, okay, this is everything you have to do, but I just want you to start paying attention to something. If I took the slope, got the slope of the right branch, I could see that it's negative, right? Negative 3.2 minus negative 1.1 over negative 1 minus negative 2. That's going to be negative 3.2 plus 1.1 over 1. That's going to be negative 3.2 plus 1.1. That's going to be negative 2.1. Okay? Then if I took the slope of the left branch, I would be using those 2 points right there. Negative 1.1 minus negative 3.2 over negative 4 minus negative 5. That's negative 1.1 plus 3.2 over negative 4 plus 5. That is 2.1 over 1. That is 2.1. So, you know you at least what looks like computed these accurately, because you should be getting branches that are positive, and I should say opposites of each other, 2.1, negative 2.1. But this number should look familiar to something up here, okay? I'm not going to say anything yet, but we'll get there eventually. Okay, so let's do 2 more. So that was number 1. Number 2, let's do f of x equals, we'll do 5, 6 times the absolute value of 3x plus 1 minus 4. Okay, so first thing we're going to want to get is the vertex. So the vertex is going to be based on when does this evaluate to be 0. So whatever the x-coordinate is that makes 3x plus 1 equals 0, that is the x-coordinate of your vertex, because that's going to give you that unique point that we talked about. So if we take away 1 from both sides and divide by 3, we get x equals negative 1/3. So the x-coordinate of the vertex is negative 1/3. Now, the y-coordinate of the vertex, plug in negative 1/3, okay? Now, what I don't want you doing is do not round. Do not write this as negative 0.33. Okay, I'm going to show you why in a minute. When I plug in negative 1/3, okay, I would get 3 times negative 1/3 plus 1 equals 0. That's going to be negative 1 plus 1. That's going to be 0. You do not want to round to negative 0.33, because this is supposed to be the number that makes this 0. If you round, okay, that's going to be negative 0.99 plus 1. That's going to be 0.01. Okay? Is that the same as 0? No, it's not. So please do not round your vertex. I want that the exact value, okay? That's going to make this 0 times, take the absolute value of that, 0 times it by 5, 6, 0 minus 4 gives you negative 4. So I do not want your vertex to be a rounded value. Can you round in your table of values? Yes, but do not round in your vertex. Okay, so now let's make a table of values, and negative 1/3 will go in the middle. Now, if you need to write down what the value of negative 1/3 is as a decimal so that you know where you should be picking points, that's perfectly fine. So negative 0.33, right? So I need 2 points that are smaller than negative 0.33. You do not need to try and pick values so that you see symmetry in your table. You do not need to do that, okay? So negative 0.33, I always just go with what's in the next integer. Okay, so what's the integer that's less than negative 0.33? That would be negative 1. Below that, negative 2. The first integer after negative 0.33 would be 0, and after that 1. Notice negative 1 and 0 are not equidistant from negative 1/3, so they're just not going to have the same outputs. That's okay. So it just means I have to do 4 times plugging in. That's fine. So 5/6 times the absolute value of 3 times negative 2 plus 1 minus 4. So that's going to be 5/6 times the absolute value of negative 6 plus 1. So that's going to be times negative 5 minus 4. Okay, the absolute value of negative 5 is 5. So you might want to take this and put it in your calculator. Okay, and it is okay to round this value. So what is 5/6 times 5 minus 4 going to give us? 0.1667. So we could just say 0.167. Okay, so in your table of values, it is okay if you have rounded values. That's fine. Next, input negative 1. So 5/6 times the absolute value of 3 times negative 1 plus 1. And then take away 4. 3 times negative 1 is negative 3. Negative 3 plus 1 is negative 2. So this is the absolute value of negative 2. That's 2. So this is going to be 5/6 times 2 minus 4. Put that right in your calculator, and you can round that value. And that puts us at negative 2.33. Repeating, so just negative 2.33 is fine. All right. Since I did 3 decimal places, I'll just continue with 3 decimal places. So rounding to the thousands there. All right. And so after that, I've got plug in 0. So that's going to be 5/6 times the absolute value of 3 times 0 plus 1 and then minus 4. Okay, that's going to give me 1. The absolute value of 1 is 1. So this is going to be 5/6 times 1 minus 4. Okay, if you just do it by hand, you've got negative 3 and 1/6. If you round it, you are going to get negative 3.167. Okay, and your last input is positive 1. So we've got 5/6 times the absolute value of 3 times 1 plus 1 minus 4. That's going to give you the absolute value of 4. The absolute value of 4 is 4. So 5/6 times 4 minus 4. Figure out what that is. So 5/6 times 4 minus 4 gives you negative 0.667. All right. Okay, so notice in your table of values, your y values are getting bigger from the vertex. That's because a is greater than 0 there. So now we just plot this. And negative 1/3 is negative 4. Okay. 0 is negative 3.17. 1 is negative 6.7. Negative 1 is negative 2.33. And negative 2 is 0.167. And we make our V. And the domain is all real numbers, and the range, okay, is it greater than or equal to or less than or equal to the vertex? All of our coordinates are greater than or equal to negative. All of our y coordinates are greater than or equal to negative 4. Okay, it is okay that these 2 points don't appear to be equally apart, because what we care about is just making the V shape. All we care about is this slope the same as this slope, and it should be if you did your computation correctly. So if we want to check, you don't have to write this down, but I want you to listen to this, okay? So if I do the slope here on the right branch, okay? So if I do right branch slope, that's going to be negative 0.667 minus negative 3.17 over 1 minus 0. Okay, that's going to be negative 6.667 plus 3.17. That's going to put us at 2.503 over 1, which is 2.503. So the slope of the left branch, if I use these 2 points, better be negative 2.503. So we could check negative 2.333 minus 0.167 over negative 1 minus negative 2. That's going to be negative 2.333 minus 0.167, puts us at negative 2.5 over 1, which is 2.5. So this is just, has to do with rounding. It's basically the same. And what I want you to notice is if I took 5/6 and I multiply it by what's getting multiplied by x inside here, which is 3, that's 15 over 6. And 15 over 6 is 2.5. Okay? So if you take your a value and the number that's being multiplied by x, and you multiply those two together, because those are what's actually those two values are what actually end up being multiplied by x at one point. And if you think about y equals mx plus b, m, slope, is what gets multiplied by x, okay? That ends up being the slopes. One is, sorry, I forgot to put the negative there. One is a positive, one is a negative, okay? So just some characteristics to know about absolute value other than just knowing about graphing it. Okay, so we'll do one more, and then that'll be it for graphing absolute value. All right, so number 3. Okay, so I have f of x minus 1.2 equals negative 3.1 times the absolute value of 2.1x minus 1.7, take the absolute value of that, and then plus 6. So this one looks a little different than the other ones because f of x is not isolated yet. That's a problem because what we want is our inputs, our output isolated, so that we say, okay, when I calculate this, it gives me f of x. So how do I get f of x by itself? Add 1.2 to both sides. So you can combine it with like terms. This you can't combine it with, but there's a constant term, right? Two constants can be added together. So that's going to give us 1.8. And so now we're ready to go. So we want to get the vertex. So what I need to know is what makes this expression 0. Now, since this is already a decimal, you're going to give your answer as a decimal. So it's okay when you have decimals to give your answer as a decimal. 2.1x equals 1.7, divide by 2.1, and 1.7 divided by 2.1 gives you a long decimal. Okay, this is the only time, okay, when you have decimals. So when you start with decimals, if you round, that's okay. Now, for that not to happen, what you can just write is 1.7 over 2.1, okay? But if you gave the rounded response of 0.8095, I would accept that, okay? However, what you should really write is just 1.7 over 2.1. If you plug in 1.7 over 2.1, this is going to be 0. Okay, whoops, sorry, this is what we're graphing, this right here. Okay, let's look at that. You get 0 times this plus that, so you'd get 1.8. Okay, so in the x coordinate, you can actually just, you could write that, but I would not take off if you rounded that, since this is a decimal to begin with. Okay, so in my table of values, okay, I know 1.7 over 2.1 is going to belong right here, but that's really just 0.8095, okay? So two values that are going to be less than that would be 0 and negative 1. Two values greater, 1 and 2. Notice 0 and 1 are not equidistant from 1.7 over 2.1, so do not expect to have any symmetry here. That's fine. We just got to do a lot of plugging in, okay? So we have to plug in negative 1. We want to plug it into this function right here. So negative 3.1 times the absolute value of 2.1 times negative 1 minus 1.7 and then plus 1.8. So we want to get the expression inside the absolute value bars evaluated, and then we take the absolute value of that, which is the absolute value of negative 3.8, so that becomes 3.8, so this is negative 3.1 times 3.8 plus 1.8. So we put that in our calculator, and we get negative 9.98. Now plug in 0, so we're going to do the same thing again, except our new input is 0. Okay, so 2.1 times 0 minus 1.7 puts you at absolute value of negative 1.7, so that's going to be negative 3.1 times positive 1.7 plus 1.8. Compute that, and we get negative 3.47. Okay, plug in 1. Evaluate inside, 2.1 minus 1.7 is going to give us the absolute value of 0.4. Absolute value of 0.4 is 0.4, so this is negative 3.1 times 0.4 plus 1.8. And that's going to give us 0.56. And plug in 2. Evaluate. 2.1 times 2 minus 1.7, that's going to give you the absolute value of 2.5, which is 2.5. So we're going to take negative 3.1, multiply by 2.5, and add 1.8. And that gives us negative 5.95. And so we make our table of values. We have our table of values, so we make our sketch, which includes 5 points, so it's going to be nice and accurate here. We've got to go all the way down to negative 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And at 0.8, okay, we're 1.8. At 1, we're 0.56, okay. At 2, we're 1, 2, 3, 4, 5, almost at 6, negative 6, sorry. At 0, we're at 1, 2, 3, negative 3.47. And at negative 1, we're down at negative 9.98. Here you are. Okay, and just try your best to keep it nice and V-shaped. And if you wanted to check whether or not you did this accurately, you could take the right branch, make sure you get the opposite slope of the left branch. And if we look here, we've got 3.1, negative 3.1 and 2.1. So if we multiply those values together, okay, negative 3.1 times 2.1, it gives us 6.51, negative 6.51. That means one of the slopes should be 6.51 and the other slope should be negative 6.51. Domain is all real numbers, then check your range. Your range here is y is less than or equal to because it's facing down. Remember, whether or not a v faces up or a v faces down is a reflection over the x-axis. That has everything to do with the a value. When a is less than 0, it reflects down. Since it does, it means y is less than or equal to 1.8. Okay, so that is it for graphing absolute value functions. What you must have is the vertex identified, 5 points in your table of values, where one of them is the vertex, 2 are on the left branch, 2 are on the right branch. If you had all 5 on the right branch, first you wouldn't know where the vertex is, and it would just look like a line. You would have no idea that it was an absolute value shape. Okay? Must have those 5 points, must have your graph, must have the domain and the range.